So hello everyone, I welcome you all in my class. So pitch controller part is over. So in today class we will design the aircraft roll control, and the same we are going to implement in the MATLAB and Simulink environment. Okay. So aircraft roll control. Okay. So there is a slight difference between control and controller. So controller is like some control approach you are following, like PID, LQR or any other, and control you are talking about roll. Okay. Including the dynamics and all methodology, everything. Okay. Now the first step is write the dynamical equations. So like in pitch case, what we have written, my I q dot, right? So in this case we will write mx ixx p dot, right? So this is the pitch motion and this is roll motion. Okay, right or left. Okay, so you can write mx equal to ixx into p dot, where is ix is moment of inertia about the x-axis, because you are rolling about the x-axis, right? P is a roll rate. Okay, p is a roll rate. Okay, and p dot is a acceleration, angular acceleration in the roll axis, right? And mx is the moment, aerodynamic moment. So aerodynamic roll moment you can write, you can bring ixx, this you can write half, rho is a density, v is a velocity, v square, s is a wing area, and here you will take a span b and then rolling moment coefficient. So in the pitch case you have taken half rho v square sc into cm, right? And cl is a rolling moment coefficient, right? So this you can write half rho v square sb, span this cl, because cl will be function of many parameter. For example, cl naught, cl beta into beta is the function of beta, beta is a side slip angle, so cl beta is will decides the actually whether you are stable or unstable in roll case. So cl beta is negative, right? Cl beta into beta, and plus what you can add, damping term, right? Clp into pb by 2v, right? And since lateral and directional are coupled, so when you take a roll motion, obviously the ya motion will happen. Okay, so you can write CLR RB divided by 2V, although during control design process we will neglect this coupling term, okay, and treat as a disturbance. And last what you can write, CL delta A into delta A and plus CL delta R into delta R. Okay, what is the coupling term here? CLR, right? And CL delta R. That means when you are deflecting basically aileron, you will have a roll moment due to aileron as well as, and okay, all right. Okay, so what you are going to neglect in control design process, you are considering the pure rolling motion, right? Okay, so CL naught you will consider, because CL naught, I mean to say, when you have any kind of a roll rate or beta, then you are going to have a roll moment unnecessary, this CL naught will not come into the picture. Like for example, if you design any kind of UAV and all, if there is any kind of manufacturing default and all, so actually you can get CL naught value, right? Okay, now here you assume your beta is 0, so this term will also 0, right? And there is a no coupling involved during the control design process, we will treat as a disturbance. So this part also you will consider as a 0. Okay, and since rudder part also, since coupling you are not taking, okay, so you will get 0. Okay. So what is the remaining? The remaining thing is P dot, and here you can write half rho V square SB divided by IXX, and here you can write CLP PB divided by 2V and CL delta A into delta A only this term, right? So here you can write this as A, so you can write A into CLP PB by 2V and CL delta A into delta A. So you take a Laplace transform, okay, take Laplace transform, you will get S P of S A CLP B by 2V P of S and plus CL delta A of S. Okay. So what you can write further? You can write S minus A CLP B by 2V A CL delta A CL delta A, and this you can write PS by delta A of S, right? Please check. A in S minus A CLP P by 2V. This becomes your plant. Okay. Now, if you go back to my stability, flight control and stability lecture, you can find out the CLP value and CL delta A value how we have found out. Okay. Now, is there any kind of oscillation will be there? Can you anybody tell? This is the first order or second order system, right? There is a no square term right here, so that means this is not the S square, right? So first you will not get any kind of oscillation. And this part, the pole, this is called in the pole. It is negative or positive? Just see, negative, right? So if you go back to my lecture, you can see I have estimated a CLP for tapered and rectangular. In the rectangular case, it is coming almost CL alpha of the wing divided by 6. So CL alpha roughly you can consider 2 pi, almost near to 6. 6 by 6 with the minus sign become minus 1. So this will become minus 1. Okay. A is positive, half rho V square S B divided by IXX, right? So that means A is positive, this is positive, B is positive, 2 positive, V positive. That means overall CLP is negative, so this sign become plus. So S plus is there, so pole will be negative. So that is why when you take a roll, suddenly you bring back, right? That's the math is also telling the same. Okay. Now with this transfer function we can draw the block diagram, right? Okay. So we can consider here the block diagram like this. We can draw A CL delta A S minus A CLP B by 2V. That is our plant actually, right? And when we are giving delta A, we are getting P, right? And when we are integrating P, we are getting phi, roll angle. Okay. So here you can take a feedback and you can multiply here, and here you can take a feedback, that will be phi command, and here you can use PI controller. Okay, and here you take a feedback, some gain K value. Okay. Okay, and before supplying to the delta A, you will put the physical limit, rate, position and actuator dynamics. So this is clear, right? How simply we have drawn. Plant, you are getting P, integration you are getting phi, P I am taking the feedback and also phi I am taking the feedback, summing here, okay? and this I am using PI controller, and this is the physical limit. Don't confuse with the PI and PL. Here P means physical limit, here P means proportional gain. Okay, so that is how beautifully you can draw the control architecture. Okay, things are clear, right? Now we are going to implement the same in a MATLAB and Simulink environment. And one more thing, if my system is so much stable, no oscillation, so at least we no need to put any kind of feedback gain here. Already so much stable, no oscillation, right? Only real negative part, no oscillation. Okay, so why we should care about this gain? We can put even 0, the things will work, and we will see in the Simulink. Why we will put 1? If you put 1, that become maybe dangerous also. You are not taking the account of that feedback gain, so that means you are put 0 instead, because in open loop your system is stable so much, right? No oscillation. Okay, real part negative, right? And that too on the real axis, right? Okay, we are going to implement the same in the MATLAB Simulink. Okay, so now we'll implement in the MATLAB and Simulink. We'll see how the role controller will respond. Okay, so for example, let's say this is a level wing, and you just think as a level, and when you take a roll, so how much you have make an angle with respect to the level position, that is called roll angle. So that you want to control, for example, 10 degree, 20 degree, 30 degree, 60 degree. Okay, that is how the aircraft takes ER, right? Take off from a Delhi. If you want to go to the Bangalore, you cannot go straight, right? Okay, let's say Bangalore is located here, take off and take a turn. So that is a there you will use a aileron to roll the aircraft, and then centripetal force will L sin phi will try to take you in a circle, and that is how you take a basically So roll control is very important, that I am trying to say. Okay, so now you can see here I have created one script file here where I have listed all the parameters. So just I wanted to tell you that we have taken a SS glider aircraft. You just search on a Google sinus glider, you will find out the parameter, span, everything and all, wing area. So you can see the wing area is 12, span is B, and IXS you can actually estimate if information is not available, 1350 kg meter square. Trim speed I have considered as a 45 meter per second, and CLP I have estimated -1. If you go back to my previous lecture, you can actually find out for the taper wind case that can be more than 1 or less than 1. Okay, for a simple rectangular case, CL alpha by 6, when you take CL alpha 6, you will get around -1. Okay, now, and CL delta A, again you go back to lectures and find out that CL delta, how we have found out. Okay, that CL delta depends upon how big your aileron and where it gets placed. If it is too far from the root, you will have more CL delta A. If aileron area is more, you will have more CL delta A, right? Okay, so already explained to you that part. Now, during the theory part, we have found out, right, A equal to half rho V square SB by IXS, right? Same you can type here. B equal to ACL delta A, same you can actually type here. Okay, and then finally we got that transfer function we have found out, right? A CL delta A divided by S minus A CLP P divided by 2V, right? So that A CLP B divided by 2V you can consider as a A1. So A1 equal to minus A CLP B divided by 2V, you can name it just to make it a transfer function. And in MATLAB you can write G underscore num equal to B. That means that is a numerator part, and that you can write denominator part as a 1 into A1, because coefficient of S is 1. Okay, and same you have taken a A1. Okay, in order to avoid minus sign, you have taken A equal to minus A CLPB divided by 2V, right? Okay, all right. Okay, now, and figure 1 I have given R locus G. That means how will you locate the actually pole location, right? So you can give the R locus G command and you can find out the root locus. Okay, and when you run this script, you will get one plot. This is the plot where you can see the pole location is in between -20 and 30. If you, to be very precise, you can see here minus 28 point something, around -29, and this is a, that part is a 0 location. That's not a concern here. Okay, now when you go back to the Simulink, so in Simulink what we have done, we have put as a transfer function. Okay, so now when you type here, for example, when you type here TF. Okay, so transfer function you will get transfer function block. Okay, and here you can actually enter the value of B and enter the value of A like this. For example, let's say when you type B here, the B will come here. Okay, this B. Okay, so like that actually you can construct the transfer function. Okay, so that is actually very straightforward here, I mean to say. So constructing the transfer function is okay, right? Okay, right? B divided by S plus A1, and B and A1 already we have defined in a script file. Okay, now this is a rate limit, and this is a position limit. When you click this, for example, this is a position limit. What position we have given? 30 and minus 30, right? So aileron can deflect plus 30 and minus 30. Okay, and what is 10 degree per second. Okay, sorry, rate limit. So first rate limit comes and then position limit. You can put actuator dynamics as well. Okay, now this is the open loop. You are giving aileron. For example, here is the input. Input means what? Aileron, right? So 1 degree you have given. If you run this file, you will see how it will look like. What do you mean by this block, step block? Okay, so you will see from 0 to 1 you know have not given any kind of input, and then you have given 1 degree for a 1 second and then bring back the aileron. So this is how you will check the response, right? Let's see how my response is coming. So this part is clear, right? The aileron you have given. Okay, and when you integrate P you will get the roll angle, right? So you will get first you will see roll rate. So obviously when you bring back the aileron at after some time the roll rate will become 0, right? Now it is 0, right? What will be the angle? Some constant value will be there, right? So this is the roll angle. If you give more aileron, more angle will be there naturally, right? Now this is the one case. But are these responses controlled? No, right? So we have to control using PID. Okay. So first we will take a plant, and in theory what we have done, taking the feedback and then joining here. Okay, but as I said, because it is already oscillation is not there, real part is only there, so no need to take a feedback gain, no need to improve the damping. What is the purpose of feedback gain? Stabilization, right? Improving the damping, right? You have a damping one, why we need feedback gain, right? That is why I have put 0. But you will improve the response, that is why you have taken the PI controller. P, this is a P controller. Okay, for example, you have integrated, taken the feedback, and error is going to the P and I controller. P you have taken 1, and I you have taken some percentage of a P. What is the percentage? 5%. Okay, so this is the 5% of a P value. You may increase P value, I value automatically will get updated. Okay, let's run and see how the things are coming. Okay, and what you have commanded roll angle? 5 degree. So at the end you should get 5 degree roll angle, right? Without any kind of unwanted behavior, right? So when you run this, you will get this roll angle. How much? 5 degree. Perfectly you are getting 5 degree, right? In less than or around 3 seconds, right? So just tell me, when I increase gain K, what will be the response? Faster, right? Now what I will do, I will increase the gain. I will just double the gain. Okay, okay, and okay. So here you can see the response. How much you are getting? 5 degree, right? But with overshoot, right? And okay. Now let's command some other value, 60 degree. 60 degree. Okay. So you will get 60. See, this is a physical limit we have put, right? Rate limit. If I remove the rate limit, you can get the immediate response. See, how much time I am getting this? 48, right? 50. And what is the rate limit? 10 degree. Okay. So at least 6 seconds it will take, 10 degree per second, right? That is if it is very fast. Now I will remove the rate limit, and you will see how far, at least less than that, and you increase the gain, let's say you increase the gain. Let's say become 1. Okay. Perfect, right? Now it is clear, right? What is the significance of the rate limit? So always in control design, try to include the physical limit. Always. Okay. Now I will put the rate limit here. See, this is the perfect response, right? Less than 3 seconds. People will be happy. I have designed the roll control. I am just putting the rate limit here. Rate limit, and this gain was 1, right? See this kind of response. Okay. And when you take 2 gain, see this response. Okay. And when you remove this rate limit, perfectly working. So that is why there is a difference between reality and what you are doing in a, I mean to say, even if you are modeling something, try to include the reality as much as possible, right? So you can see only one things you are not including and you are getting beautiful response, and then we are including, your gain is changing, right? Now, and at this stage when you are putting this, I mean to say, uh, gain, this is, so this will not be controlled response, so you have to decrease the gain and then only you will get the response like this. So that is, you can say, the perfect response. Okay, you don't have any doubt in the block diagram, right? You can check the rate also if you want. I mean to say, you just type the scope here. Scope rate should be 0, right? You can run from here also. See, the rate is increases and then 0. For example, if you want to command, rate will achieve some value. Once it is achieved the 60-degree, so rate becomes 0, but aircraft will have a still 60-degree angle. So do not confuse with that key, if there is an angle, there should be rate. Okay. So try to understand each and every parameter. Okay. Now go back to your home and change the CL delta A, change the CLP, and play with this code and enjoy. I mean to say, when you see, for the common sense, when you increase CL delta A, your aileron control power will increase, right? So actually, you can actually control while taking less time as compared to what you are actually controlling here. Okay, rate limit. So then you can take the actuator, powerful actuator. Okay, where the rate limit is more. Okay, so that kind of sort of thing is you can play. Change the parameter again and just play. Okay. So for example, in theory, when CLP value is more negative, that means root locus will be more far from the origin real part, and in that case you will need more control to, I mean to say, stabilize the aircraft, to control the aircraft, right? And if it is close to origin, small aileron deflection can control the aircraft. So this kind of feeling you have to have, stability part as well as the control part. These are two interrelated. More stability, more control is required. Little less stability, less control is required. So I mean to say, you can play with the parameter and all. And since I assume that this, you are familiar with this step block and this radian to degree conversion, scope block, everything, I mean to say. But even if you are not getting anything, you just ask me, I will explain to you, right? Each and every block is available here. You can actually type, for example, if you want to get this position block, you just type saturation. Okay, saturation block will come. Okay, you can enter the value here. Okay, so all things are available in this. Even if you have doubt, you can ask me. Okay, so we'll meet in the next class. Thank you so much.